Today we are going to see about Artificial Intelligence Unit 4 Planning. So we all know what is meant by planning. Planning it is nothing but a sequence of actions to achieve a particular or a specific goal. So it may be answering to the questions how and when to act. So planning helps in making decision in a structured and optimal way. So for real-time example, if you are considering a delivery robot planning the most efficient route, avoiding the obstacles and routing traffic areas and find a path is an example for planning. Next, there are two types of planning basically. So it may be classical planning and non-classical planning. So in classical planning, the environment may be fully observable, deterministic, finite, static, and discrete. Whereas in non-classical planning, it is the environment is partially observable or stochastic environment. So problems. So planning problems it is defined by domain models, initial states, and goal state. Let us consider the robot example. So in domain model, so it describes the available actions and the preconditions and the effects. Whereas initial state, it is nothing but the current configurations or a scenario. Whereas the goal state, it describes the outcomes. That is the robot at charging station may be the goal state. So initially for initial state, the robot will be in a position 0, 0, whereas in goal state, the robot will be reaching to the particular location. Components of planning systems. There are mainly five components in a planning system. First one is rule or actions. Next one is action execution, recognizing the goals reached and handling the dead end and refining the partial solutions. So here rules are actions. It may be the set of actions which can be made on a particular environment. Action execution is something but the plan is being executed in the particular environment, whereas the goal reached, recognizing the goal reached is nothing but the goals are reached in a particular environment. Handling the dead end is sometime the problem cannot be solved and it will be reached to the dead end, that is called as dead end solution. Handling the dead ends, redefining or refining the path solutions. Once the dead end has been occurred, so we have to refine the path solution, so that is represented as the refining the path solution. Next is state representation. So here state representation is a facts using the logics. For example, let us consider this as a refrigerator. It contains eggs and the milks, so it can be represented by using a conjunctive terms, that is milk in the fridge and egg in the fridge. So here it is represented by a conjunctive statement, and so we can represent it by means of a proportional logic or a first order logic. Goal representation. So the goal is nothing but the desired state specifying the satisfying the specific conditions. The goal achieved when the facts matches or the desire for the desired conditions. So for example, an autonomous vehicle reaching the destination point with the minimum fuel, it may be a goal or a goal representation. So action representation. Action has two parts. One is precondition and one is post condition. So the action derives C, that is we are driving car from the location, from location to the to location, that is destination location. So here in action we have two parts, one is precondition and one is post condition. So precondition is nothing but at where the car is starting from, it is starting from the location, from location. So we need a car also, so it is represented as car of C. So at C is the start, C is the car, and from is the start location, and it is represented by means of a proportional logic and car. We need a car from start from the location. Next is post condition. The post condition is that this precondition becomes negated and we have to reach to the destination. So this becomes a negated statement and we have to reach to the goal, that is at of C comma 2, that is destination. The car has reached the destination. Then application of the plannings in AI. It is used mainly in robotics, gaming AI, logistics, military applications, and spatial machine applications. So these are all the applications of languages. So next is planning languages. So the language it is used to describe the planning language is mainly used to describe the actions, preconditions, and the effects. So this actions, preconditions, and effects can be represented in a certain notation that is called as planning languages. So as we see in the state representation here, this can be one of the representation where the milk contains the fridge and so milk contains sorry fridge contains the milks and the eggs. So this is regarding the goal representation. So goal can be represented the car when reaches its destination. So this can be represented as at of C comma destination. So accent representation as we seen earlier, it will be having two conditions, that is preconditions and the post conditions. Action of drive C comma Chennai to Attur. So precondition is that car starts from the Attur, that is Chennai, and we need a car, and the post condition is that this Chennai car starting from Chennai becomes negation part and it reaches to Attur, that is Atta Sikama Attur. So it is a kind of representation. So planning languages, that is we are using different languages, the stripes, ADL and PDDL. So stripes is nothing but stand for Research Institute Problem Solver. It is a kind of planning language, and ADDL is nothing but action description language, and PDDL is nothing but planning domain definition languages. So strips. So here strips uses the makes use of the first order predicates. So strips allows functional free literals. So for example, let us consider a robot. The example involves a robot, a cup tea, and a guest and a two rooms. We want the robot to get the tea and give it to the guest. So here let us consider the robot. This is a teacup. This teacup must be taken by the robot and must be handed to the user. So it has two rooms. From this room, it has to reach to this room and it has to be given to the guest. So it is a kind of problem. So it can be represented by using different, that is, we can use it by using first order logics and functions. So mainly we'll be seeing about PDDL only in this unit. So PDDL is nothing but problem definition language. So it is a standardization of a planning language. It is defined by the researchers as a standard language. We said it is a superset of strips and EDL that allows features like, so here this PDDL will allows the features like type specification, negative preconditions, the add and the delete list can be conditionals, and in some cases it allows numericals also. So for us, as we seen earlier, planning, if we see in daily routine planning, we can make it as planning is a part of daily routine. So for example, let us consider the studying schedule. It includes hours, managing the household task, etc. For example, in our daily routine we may have the schedule for studying and also for having doing the household works. So it involves constraints like time, priority, and availability. So these are all real-time examples for planning. Oh, so let us explain the PDDL. So PDDL is nothing but problem planning domain definition language. A state is a conjunction of fluent. So here this PDDL contains the different fluent with conjunctive in between. So actions. So action is or described by a set of action schemata. So conscious descriptions describes which fluent changes. So action schema, it consists of schema name and list of variables in the schema and the preconditions and the effect. It is also called as effect is also called as post condition, also known as post conditions. So PDDL. Let us consider this PDDL. So here PDDL. So action of fly. So fly, the plane flies. Here the action is fly. So plane flies from the location from and to the location where it has to reach. So here for the preconditions, we have to note down the precondition. Plane, we need a plane for flying. So it has to fly from the airport from, and airport to, and at of P comma from. Where it has to start from? It has to start from the source. Next, effect. What is the effect? It has to be negated. Which has to be negated? Where the plane has been started has to be negated. Then and at of P comma 2. At of p comma 2 is nothing but the plane reaches to the destination. So it is the action schema. So action instantiation is nothing but you have to replace it with an examples. So SFO and JFO. So San Francisco, and we have to have another airport, that is John F. Kennedy Airport, which is represented as a source and it is as a destination. So in the meanwhile, it is as we explained in the previous schema, you will be having the initiation also. The languages of planning, PDDL. PDDL must has a precondition, efforts, action list, delete list, and the result of action is an in a state. This all be represented in a PDDL. Okay, language for PDDL. So planning a search problem. All components of a search problem may initially have an initial state, action function, result function, and a goal state. Let us consider a cargo problem, cargo, airport, and a plane problem. So here there will be airport 1 and airport 2. From airport 1, the cargoes has to be loaded to the plane P1 and it must be transferred to the airport 2. In the meanwhile, the cargo C2 has to be loaded into the flight 2 and it must start from the airport 2 and it must reach to the airport A1. So this is airport 1. So this is the problem. So this problem is called as air cargo transport problem. So initially the PDDL will be like this. So you have to have a planning and you have to have a solution. So initial, what is the initial state? At what is at is an action here. Then what it has to do, the cargo C1 is at SFO. SFO is nothing but San Francisco Airport. That is the airport 1. Then cargo 2 is initially at KJF, sorry, JFK. JFK is nothing but John F. Kennedy Airport. Then the plane has to start from SFO and it has to reach to plane has to reach us at JFK. Then you'll be having cargo 1, cargo 2, plane 1 and plane 2. Then airport is JFK and airport is SFO. Goal is nothing but we have to reach where we have to reach. C1 has to reach as JFK and C2 has to reach at SFO. The action here is we are having three actions. What are the actions? Load, unload, and fly. Load action is nothing but cargoes are loaded into the plane and the plane it starts from the airport and moves. Then unload is nothing but the cargoes are being unloaded from the plane and it is moved to the airport. And the action is that the plane flies from airport from 1 to. So these are all the PDDL representation which uses the FOL with the conjunctions. So here is the solution. Load of C1 comma P1. What is something but cargo 1 is loaded into the P1, that is plane 1. It starts from the San Francisco. Fly of P1 comma San Francisco comma JFK. The plane flies from San Francisco and reaches to John F. Kennedy Airport. Then it unloads. What happens? It unloads. Where it unloads? It unloads from the plane P1, the cargo C1 in the John F. Kennedy. Similarly for the flight 2. That is for cargo 2 is also loaded in the flight 2 in John F. Kennedy Airport and it flies to the San Francisco Airport and it is unloaded in the San Francisco Airport. Next problem is spare tire problem. Here you will be having three conditions. One is we assume that the car is parked in a particular bad neighborhood. When we leave that car in a bad neighborhood, the effect is that overnight the tire disappears. That is the flattened tire will be removed from the axle and it will be stolen by the neighborhood. So the problem is nothing but spare tire problem. So this is also a kind of problem for planning and it uses the PDDL for representation of that problem. Next problem is block world problem. Here you will be having three blocks on a table. So you have to, this is the goal state, this is the initial state and this is the goal state. We have to assemble the blocks in such a way that we have to reach the goal. So PDDL will be represented like this for the block world problem. Okay, planning with the search space. So you'll be having two algorithm, that is forward state space search, that is progression, and the backward state space search, that is regression. So here the description option actions in a planning problem and specify both preconditions and the effects. So it is possible to search in both the direction, either forward from initial state to backward from the goal, and also we can have a vice versa also, that is forward chaining, that is forward and backward. So in forward, problems formulations for progression. Progression is the initial state. You'll be having a problem, planning problem, actions, application of the current state, first actions, then you'll be adding the past literals. Then the goal state is we have to reach the specified goal. Next is pathcast is we have to assume that the pathcast is 1. So you'll be having the diagram here. Let us consider this is the diagram. So at of star of I comma a, here it is nothing but we have to start from the start state and we have to reach the goal state. So here, for example, let us consider the flight problem. So here at of you'll be having a flight in the car in the airport. That airport you have to make the flight to fly and it has to reach to the particular destination. So this is from, we are starting from the start state, we'll be performing an action and then we'll be moving to the goal state. So this is regarding F triple S algorithm. So this is the algorithm. So this algorithm will be having initial state and an empty plan. Then you'll be having a loop. So you'll be having certain actions. The actions will be leading to the particular goal. Regression is nothing but reverse of that is backward state space search. Here you'll be starting from here, that is here, which is nothing but from goal state you have to start, then you have to perform the action and then you'll be reaching to the initial state, that is B triple S algorithm. So this is regarding the classical planning where you'll be having a conditions, based on the conditions certain actions will be performed. Next is heuristics for the search space, state space search. Here you will be having heuristics algorithm. So here for each heuristic, that is heuristic planning, neither a forward backward search is efficient without a good heuristic function. So we don't have any, if you don't have a heuristic value or a heuristic function, both forward and backward search is inefficient. So for example, let us consider A star as a best first algorithm. So which uses an evaluation function f of s is equal to g of s plus h of s, where g of s is called as a cost to reach the state, that is goal state, and h of s is that admissible or optimistic heuristic function. A heuristic function h of n is admissible if h of n is less than or is equal to h power star, that is h star of n, whereas h star of n is nothing but actual optimal cost from the goal node. So here in heuristic planning, you'll be having the heuristic value for reaching a particular goal. The form of problem relaxation. So here we should have a problem relaxation, that is relaxed problem or a problem relaxation. A techniques for admissible heuristic is called as problem relaxation. The cost, the exact cost for the solution is to be relaxed. The h of s can be relaxed, which is a problem of relaxation. So here the problem of relaxation, we will be removing the constraints, some constraints from the original problems to make the problem solve it easier. So relaxed problem has fewer restriction and it is easier to compute and gives a solution cost that is less than or equal to the original problem. So forms of relaxation problem. Relaxation problem is normally in a problem you will be relaxing certain condition. That conditions will be leading to solve the problem in an effective way so that we can easily solve a problem. So this is regarding the uh, that is heuristic plan problem, that is planning. Next is hierarchical planning. A form of task based planning is called as hierarchical planning. So we'll be having a higher level task. The higher level task will be decomposed into a simpler subtask, also called as hierarchical task network. It is also called as, this hierarchical planning is also called as hierarchical task network. This HTN planning. The model how human naturally performs a function, that is from abstract to concrete. So here it contains a set of high-level tasks. The task will be decomposed. Decomposition is nothing but breaking down the task into a smaller subtasks. Then you will be having the primitive actions. What is the primitive actions? Primitive actions, a task cannot be further decomposed. Where a task cannot be further decomposed, that is called as primitive actions. Then at last we have to construct the HTA. That is HTN is nothing but hierarchical task network, a tree for a tree of tasks and actions. So let us consider organizing a birthday party. So here the birthday party, the high level task is to organize a birthday party. Here this high level task can be decomposed into sending an invitation, arranging the food, and planning the entertainment. So this what we can do, this is sending an invitation is a primitive actions. It can be divided into primitive actions such as this subtask sending invitations can be divided into different sub actions. This primitive actions such as call caterers, then send a mail, and we can hire a DJ. Like that we can decompose us into primitive actions. This primitive actions cannot be again decomposed. Then how to draw a planning, this HTN planning works. So starts with the top level task, then use the methods of decomposition and repeat the decomposition until the primitive action is achieved and execute the primitive actions in order to achieve the goal. Here's this is an example for a black hole problem using an HDN network. So here, advantages of HDN planning. Suppose supports domain-specific knowledge, handles complex problem via decomposition, and produce flexible and reusable plans and more initiatives than flat acting on planning. So this is regarding hierarchical planning. Next is uncertainty and basic probability notation. The second part of the fourth unit contains the uncertainty and the basic probability notation. What is probability? So probabilities are used to compute the truth of a given statement written as a number between 0 and 1. Normally the probability value will be 0 and the 1. That describes how likely an event which is going to occur. For example, 0 indicates the impossible events and 1 indicates the certain events. For example, if you toss a coin and there is a possibilities of getting a head. So head means there is a possibilities of getting in a coin. You will be having two sides. One is head side and one is tail side. So here the probability of getting the head side is 1 by 2 and the probability of getting the tail side is 1 by 2. So the sum of the both options leads to 1. That is probability, individual probabilities put together when it is summed, it leads to 1. So probability based reasoning. So understand from the knowledge how much of uncertainty is present in an event. So this is regarding the probability, that is basic probabilities. So there are different types of probability, the different types of variables in probability. One is Boolean random variables, discrete random variables, another one is continuous random variables. So atomic events, prior probability, conditional probability. So these are all the basic probabilities we'll be having in an uh, probabilities. Okay, next is uncertainty. What is uncertainty? So uncertainty is a lack of complete information. So for example, let us consider a car is going in a mist road. So we can't predict whether a road diverges or not. So it is difficult to get the clear conclusion. Here some informations are lagging because there is a fog which leads to the taking a decision on a particular on a right time. So there is no enough information in data to make a decision. So it is a kind of uh, situation is called, that kind of situation is called as uncertainty. For example, in an AI system analyzing low quality HD images may struggle to detect the anomalies accurately. So here the images are low quality. To detect the anomalies, it will be very difficult. Causes of uncertainty. So uncertainty may lead to unreliable sources, experimental error, equipment faults, and temperature variations and climate changes. So these are all the causes of uncertainty. Probability reasoning. So here probability. So normally probability can be defined as a chance that an uncertain event will occur. So uncertain event will occur, that is a chance of making a probability. For example, P of event is equal to number of favorable outcomes divided by total number of possible outcomes. So how many favorable outcomes can occur? This can be divided with the number of possible outcomes. So this is regarding the probability. So probability of occurrence is equal to event and occurrence. Occurrence is equal to number of desirable outcomes divided by total number of events. So the probability of not occurring that event plus probability of occurring event is equal to 1. Next is probability notations. So you'll have different probability notations such as P of A is nothing but probability of event A occurring. P of A dash is nothing but event not occurring. Probability of an event A not occurring. P of A intersection B is nothing but probability of both A and B occurring at the same time. P of A union B is nothing but probability of an entire, sorry, either event A or B occurring. P of A intersection B is nothing but probability of A occurring but not B occurring. A dash union B is nothing but probability of either A not occurring or B occurring. Probability of flipping a coin. So event here it is flipping a coin. Favorable outcome is landing on head. So the outcome will be 2. Total outcome is 2, head or tail. So probability of head landing a coin on a head is nothing but 1 by 2, that is 50%. Similarly, rolling a die, if you are getting you want to get an even number, that is 2, 4, 6, there will be 3, that is 3 by 6. Total number of outcome is 6, 3 by 6, that is equal to 1 by 2. Conditional probability. Next is important topic, that is conditional probability. Conditional probability is a probability of occurring an event when another event has already happened. The cloud has been black clouds has been formed. As a result of this, there may be a possibilities of rain. So P of A given B is equal to P of A intersection B divided by P of B, where P of A intersection B is nothing but joint probability of A and B, and P of B is nothing but marginal probability of B. So these are all the examples, just you can go through. Next is Bayesian inference. Bayesian inference is the core probability reasoning techniques where the prior probability, that is prior belief or initial probability, is updated with the new evidence to compute the post probabilities. For example, applications of probability reasonings can be used in medical diagnosis, weather forecasting, natural language processing, autonomous vehicle, and recommendation systems. Next is Navy-based classifier. So Navy-based classifier is a supervised machine learning algorithm that predicts the categories of data using probability. Navy is nothing but it assuming the all data given in the data sets are completely independent, and Bayes is nothing but it defines the Bayes theorem. So Bayes theorem is something P of A given B is equal to P of B given A into P of A divided by P of B. This is Bayes theorem, where P of A given B is nothing but posterior probability, which is going to occur after the event. P of A given B is nothing but likelihood, and P of B is nothing but prior probability, and P of B is nothing but the marginal probability of B. The types of Navy-based model: Gaussian Navy-based model, multi-nominal Navy-based model, and Bernoulli Navy-based model. Application of Navy-based model can be used in swarm reduction. Next is sentiment analysis, document classification, medical diagnosis, and recommendation systems. So this is regarding the Bayes theorem. So Navy-based algorithm, there are 4 steps. One is you have to calculate the probability, that is prior probability you have to calculate P of A. Next we have to calculate the likelihood probability, that is P of B given A. Then you have to apply the Bayes theorem to calculate the posterior probability, make the prediction based on the highest posterior probability value. So let us consider an example, that is data set is given. Here the temperature data set contains 3 main items. One is temperature, sky, and the rain. The temperature has 2 classes. One is 3 classes. One is hot, mild, and cold. Sky, it has 2 classes. One is cloudy and sunny. Another is rain may occur or may not occur. So our goal is to predict if it will rain on a new day with temperature is equal to hot and sky equal to cloudy. So we have to predict our goal, that is we have to calculate the posterior probability. So prior probability, we have to calculate prior probability. Yes, so how many S's are here? 1, 2. 2 S's are there. How many no's are there? 1, 2, 3. 3 no's are there. So totally how many outcomes are there? 5. So probability of rain equal to S is equal to 2 by 5, that is equal to 0.4, and probability of rain equal to no, that is equal to 3 by 5, that is equal to 0.6. Next we have to calculate the likelihood function, that is temperature class has 3 subclasses: hot, mild, and cold, and sky has 2 subclasses, that is sunny and cloudy. So this is for S cases. Yes, totally how many S's are here? Here this is 2S. So how many temperatures? Temperatures, how many hots are there? Only 2 hots are there. Out of 2 hots, how many S are there? Here 1 hot and here 1 hot. This hot is S, so 1 by 2. Then how many no's are there in terms of hot? Here we have only 1 hot as no, that is 1 by 3. Total no's are 3. So 1 by 2 and 1 by 3. Mild, how many miles are there? Totally 2 miles are there, out of which 1 is yes and 1 is no, therefore 1 by 2 and 1 by 3. Cloud, how many cloud? Cold, how many colds are there? You have 0 colds, that is 0 cold with yes, and 1 by 3, that is 1 cold with no. Next regarding sky, we have to calculate sunny and cloudy. So here the sunny value for cloud which contains yes is 0, there is no sunny with yes probability of rain. Similarly, sunny with no condition for rain is 3. So 3 bar 3. Cloudy with rain condition as yes is 2 bar 2, and cloudy with rain condition as no as 0 bar 3. At last we have to apply the Bayes theorem and you have to find the probability value. So here we are applying the Bayes theorem. So P of hot equal to S is equal to 1 by 2, that is equal to 0.5. The cloudy equal to S, that is 2 by 2 equal to 1. P of S, that is equal to 3 by 5 is equal to 0.4. You have to multiply all those things and we'll be getting the value as 0.2. Therefore, we have to apply the probability for Bayes theorem for no also. You have to apply. So here no, what are the conditions for no? We have to get the value as 0.3. That is hot equal to no, cloudy equal to no is 0, and P of no is equal to total no is equal to 0.6. Therefore this is 0. So based on these two values, probability of rain when the temperature is hot and sky is equal to cloudy is 0.2. Probability of no rain when there is no rain, when temperature is hot and cloudy equal to sunny, cloud is equal to sky is equal to cloudy, this is equal to 0. So P of S is greater than or is equal to P of no. So here S has the greater value. So there is a high probability to make the prediction. Here rain will occur. Similarly, you can consider this problem and take it as a homework and you can proceed. So here we'll be having a data set, and based on the data set you have to calculate, you have to find the posterior probability if the weather conditions are outlook is the main class here, equal to sunny, and temperature is equal to hot, and humidity equal to normal, and wind equal to false. Can we play on the day? We have to predict. Next is Bayesian network. So what we have seen before is Navy based classification. Now we are going to see about the Bayesian network. So in Bayesian network, a Bayesian network is a posterior probability graphical model that represents a set of variables, and the conditional dependency is used among them, and it is represented by using a DAG graph, that is directed acyclic graph. So used to represent uncertainty knowledge and make a decision based on the knowledge. The components of Bayesian networks are DAG and CPTs. DAG is nothing but directed acyclic graph, and the CPT is nothing but conditional probability table. So directed acyclic graph, normally this graph contains nodes, edges, and acycle. Acycle is nothing but does not have a loop. So here burglary, earthquake, alarm, John calls, and Mary calls are the nodes. The connection between the two nodes, this arrowhead represent the edges. Directed acyclic is nothing but there is no loop like this. Conditional probability table is something but each and every node will be having a value. Those values are called as conditional probability table. So this is regarding the example burglary at home. So there will be we can consider this example. There will be old people. They are going to their son's home. They will be having an alarm. This alarm will ring when burglary has occurred or earthquake has occurred. So the grandparents has informed to the neighborhood, that is John and Mary, both has to call when the alarm has ring or earthquake has occurred. So John always call when he hears the alarm, but sometimes confuse the telephone ring with alarm and calls them too. Mary like loud music and sometimes miss the alarm altogether. So these are all the conditions. So we have to calculate what is the probability that the alarm has sound, but neither a burglary nor an earthquake has occurred, but both John and Mary called. So here we can calculate the probability, that is joint probability P of A, P of J. J is nothing but John calls, Mary calls, and alarm has ring when there is no burglary and there is no earthquake. So this can be rewritten in terms of conditional probability P of J given A into P of M given A, that is John calls when alarm rings, Mary calls when alarm rings, into P of A, that is alarm rings when there is no burglary and there is no earthquake, and P of there is no burglary and there is no earthquake. So these values can be computed from the tables given, and finally the answer will be 0.00062. Similarly for John calls. Next is semantics of Bayesian network. So normally the semantics of Bayesian networks, it contains mainly two things. One is DAC, another one is conditional probability table. Normally the probabilities of each nodes can be represented by using P of x comma 1, x1, etc. up to xn, that is equal to pi of I equal to 1 to n. Theta is nothing but here the theta it is nothing but the initial probability xi given parent of xi. So this theta can be replaced by p, that is probability. So this can, so the above equation by replacing theta with p can be rewritten as p of xi given parent of xi, where parent of xi is the parent of node xi. For the example, it is given, we have to calculate the probability when John calls and Mary calls when there is no alarm, when there is an alarm rings, when there is no earthquake and the burglary has occurred. The method for constructing the Bayesian network. The likelihood probability P of A given B. This can be likelihood probability can be calculated as P of A given B comma C into P of B comma C. Same we are going to use P of X comma X1 comma etc. up to Xn. This can be rewritten as Xn given Xn minus 1 rather than X1. What are, if you remove X1, remaining things what are will be there? Xn minus 1, Xn minus 2 etc. up to Xn X1 into this remaining terms alone we have to multiply as such like this, where we have given as such we have given these terms now like that we have to multiply these values alone. Next by chain rule. By chain rule what happens for a first we have written xn term, the next one is xn minus 1 term, then xn minus 2 term, then at last x2. x2 divided, sorry, x2 given x1 into p of x1. So this entire equation chain rule can be rewritten as p of xi given xi minus 1 etc. up to xi for the entire pi of n for I equal to 1 to n. So this equation and the above equation can be compared. So next step we have to comparing the equation. So for both the terms we are going to compare this one and this one. So this 2 has the right hand side equal. So we are going to compare this two. So what happens? So finally we'll get the answer that p of x given parent of xi is equal to p of xi. This p of xi given xi minus 1 etc. up to xi. So rules for construction of the Bayesian network. So from this we have arrived to the conclusion that p of xi is nothing but provided the parent of xi is a subset of xi minus 1 etc. up to xn. This last condition is satisfied by numbering the nodes in a way that it is consistent with the partial ordering implicit in a graph structure. Next is rules of constructing the Bayesian network. There are you'll be having in Bayesian network, you'll be having the nodes and the links. First, what you have to do, you have to determine the set of random variables. Then you have to order those random variables. Any order will work out. Any order you can use, but if the variable is ordered in such a way that causes precise the effects, then it will be better. Then link. Link, what is link? Link between the two nodes. The arrowhead represent the link. So choose from xi to xi to xi minus 1 a minimal set of parent. So among these nodes, you have to select a minimal number of parents. For each parent, insert a link from a parent to xi. We have to link a node from parent to its child. So properties of Bayesian network. What are the properties of Bayesian network? There are three different properties. One is it has no redundant probability values. Next is axiom of probability and locality structures. Then once the node is structured, that is the network is constructed. Next we have to see the compactness and the node ordering. We have to see the compactness and the node ordering. So locally structured, the compactness of the Bayesian network is an example of a sparse system. So here let us consider the node ordering one. Here first let us consider the node Mary calls. This Mary calls as a first node. Then we'll be having next node as John calls. So the John calls and alarm has a parent as Mary call. Similarly for alarm, from alarm we'll be having two nodes, one is burglary and the earthquake. So here for burglary and earthquake there will be a parent called as alarm. So if you are ordering like this, at last you will be concluding that burglary and earthquake cannot be a child, it must be a parent. So again we are restructuring. So it is one kind of node ordering. Next one is another kind of node ordering. Here we are considering Mary call as the first, then John call, then here we are considering as the earthquake, burglary and alarm. So here there will be n number of links, that is many number of links will be there from Mary calls to alarm. So here if you are doing like this, if you are constructing a Bayesian network like this, you have to construct this Bayesian network with 31 distinct probability values, so it will be somewhat complicated. So conditional independent relations in probability in Bayesian network, there are two conditional independency. First one is topological semantic, where you have to consider the node x. Here the shaded node x, no, this node depends only on its parent, not on its other nodes. So it is dependent on its parent and it is independent on its non-descendant. So it is called as topological semantic. Another is Markov blanket is nothing but the x node depends on its child, depends on its parent, and also its child, and also its child parent. So this entire circles forms the dependent node. Another one is independent. So this is regarding the semantics of Bayesian network. Next one is extract the inference from the Bayesian network. Here you will be having three topics. One is inference by enumeration, variable elimination, time space complexity, and clustering. First, exacting the inference. So normally for exacting the inference, the query variable inference system is to be compute the posterior probability. You have to compute the posterior probability distributed for a set of query variables. For a set of query variables, you have to distribute the posterior probability, where xn denotes the query variable, e denotes the evidence variable, and small e represent the observed event, and y represent the hidden variable. So this can be represented as x is equal to x of union e union y. So this can be A typical query asks from the posterior probability distribution P of x given E, where E is an observed event and X is a query variable. Exact the inference from enumeration. First, enumeration means checking the options one by one. What are all the possible options there are? You have to check the options one by one. The query P of x given A can be answered by using x given A is equal to alpha into P of x given x by x comma E, that is equal to x. X is nothing but alpha here. Alpha into P of x comma E, alpha into summation of y into P of x comma E comma y. Let us consider the truth query, that is tooth and toothache cavity problem. So here toothache is a query variable and cavity is equal to 2 is an event occurs. Similarly, second example, burglary query. So here the burglary is a query variable and John calls is the John call equal to true and Mary call equal to true is an event. So this can be rewritten as alpha. How many query variables are there? Those much number of summations you have to use. So here uh, in the hidden variable for this query are earthquake and the alarm. So the earthquake is written as the summation of E and alarm is written as summation of A into P of B comma J comma E comma sorry M comma E comma A. B is nothing but burglary, J is nothing but John calls, Mary calls, E is nothing but earthquake and alarm. Here alpha is an enumeration constant. So here this alpha is an enumeration constant, so we are taking it out. So this can be rewritten as again P of B. So this P of B given, so this P of B comma J comma M comma E comma A can be rewritten as probability of B, that is burglary, earthquake, alarm rings when both earthquake and burglary has occurs. Then P of John calls when alarm occurs and Mary calls when alarm occurs. This is P of burglary occurs when John and Mary calls. So this can be again rephrased as here uh, this hidden variable summation of E, the term related is P of E. So we are splitting and writing for entire, here the two summations are there E and A, where P of B is made as constant and is moved outside the summation, that is alpha into P of B, these two are constant. Then P of E is nothing but which belongs to the hidden variable E, and P of A with these three terms depends upon the A terms, so it is kept inside. Then next we have to construct a tree, enumeration tree. So here this enumeration tree is something but you have to keep A here, then you have to have the summation P of B is here, summation this summation is P of E is nothing but probability of earthquake is true and false. Next from here you have to start again from here, when the earthquake was true, alarm may be true and alarm may be false. Here also alarm may be true and alarm may be false. When the alarm will be true, John calls and Mary calls. When the alarm is false, John calls and Mary calls. So likewise, you have to construct the tree and finally you have to calculate the value, and this enumerated constant alpha can be calculated by using the enumerated calculation formula. So this is the algorithm for enumeration algorithm, which has two functions. One is enumeration ask and enumeration all variables. The next one is variable elimination. So here we have to replace all the probabilities with the functions. The functions f1 of B, f2 of E, f3 of A comma B comma E. So A comma B comma E. So this lower letter cases can be replaced by capital letter cases, but the functions can be differ. At last, what you have to do, we have to remove all the values based on the condition that we have to eliminate A. For example, you have to eliminate A by changing that A to small a plus negation of small a. We have to use this concept and you have to remove. At last, what you have to do, we have to form an equation that alpha into f1 of B B into f7 of B. Remaining all the variables are eliminated and we are likely to get the variable as B alone. Operations on factors and point wise multiplications. So here you'll be having different tables A and B. So here there are two options, so there will be four possible events. So f1 of A comma B, this value is given. Then again for four possible combinations, f2 of B comma C is given. Then we have to calculate f3 of A comma B comma C. First, what you have to do, you have to calculate f3 of A comma B. So you have to multiply an A and B value, f3 of A comma B. So A comma B, f3 of A comma B is, when it is true, is 0.3. Here it is 0.3. Next B comma C, f3 of B comma C, f3 of B comma C is 0.2. We have to multiply this two. then you will be getting the value. Likewise, you have to calculate all the 8 combination values. At last we can do the point-wise multiplication. Next, as we said here, from this table we can form and these values can be formed as rows and columns value. First two will be forming another one matrix, another two will be forming another matrix of 2 cross 2. Both the values will be added and it will be forming a resultant 2 cross 2 matrix. From this we will be calculating the summation value. This is called as variable ordering process. Then complexity of an exact inference. The complexity will be in which there is only one unidirection, most one unidirection path between two nodes in a network. They are called as singly connected. When there is an only one unidirection path in a tree, this is called as singly connected. For singly connected tree, the time and space complexity is linear, whereas multi-connected tree, the complexity will be exponential times and the space complexity becomes worse. Next is clustering algorithm. Here, let us consider the sprinkler problem: cloud, sprinkler, rain, and wet grass. So these two nodes can be clubbed to form an another node, that is cloudy, sprinkler plus rain. Another one is wet grass. So these two nodes join to form a node called as big nodes. These two nodes forms a common node called as big node or a mega node. So this mega node will have four possible combination because it is formed from two nodes. So this will be having a four possible combinations. So clustering algorithm is nothing but it combines two nodes to form a mega nodes in order to reduce the complexity. This is regarding the inference extraction by means of elimination of a variable and clustering the nodes. Next one is castle network. Castle Basin network is also known as castle diagram. So this castle diagram emphasizes the relationship between the cause and the effect. So this cause and effect can be drawn by using a diagram of arrows or edges. So this is used for causal reasoning. So this structures can have x of I equal to f of I into other variables. There is a relation between xj to xi. This arrow diagram can be replaced by using the functional terms. Xi equal to fi into fi is nothing but functions. Let us consider this uh, Bayesian network. Here cloudy, sprinkler, rainy, wet grass and green gas. So this can be a probability of gas can be wet or green gas. The structural equation can be cloudy C equal to, here the function is FC. FC is nothing but a function. UC is nothing but we are adding an variable which is called as unmodeled variable or an additional variable or an error terms in this structural equation. Since the node is a parent node, you'll be having only one additional node alone. Let us consider the rain node. So here rain node, the function is for, and it has a node called as C, where C is the parent of rain node and UR is the unmodeled or an error term or an additional variable. Likewise, you have to rewrite. So this is regarding the castle network. So this is the last topic of the unit 4. So thank you.